Hi. So today I want to talk about the dispersion relationship for matter waves and also a little bit more about wave packets. So to remind you, where we ended on the last lecture was we did a review of a lot of the notation that I'm going to use today. So if you get confused about what a wave number is, I encourage you to go back and look at that last lecture again. Okay? But for now, let me remind you that we're doing all of this because we're studying the idea of a quantum particle. And a quantum particle is basically one that exhibits wave-particle duality. Now remember, this only happens for pretty much small particles. Large particles have a size and mass that's large enough that their wavelengths are pretty much inconsequential. So you have to get down to tiny little particles like electrons before you can really witness wave-particle duality. Now remember that ideal waves versus real waves, it's not really the same thing. Remember that an ideal wave is sort of an infinite sinusoid. That's what most people picture. But real waves are always localized in space. And waves that are localized in space are wave packets. So most of the waves that we talk about are going to be wave packets. Now last time we reviewed Fourier series and talked about how to make a real wave packet, you'd have to sum up lots and lots and lots of ideal waves. Today though, just for simplicity's sake, we're going to talk about what happens when we add just two together. And remember that all of the things that we talk about when we talk about just two waves being added can be extended to the idea of our Fourier series mechanics. Okay, so let's take two waves that are in the same place at the same time and combine those waves to make a packet. Now, when two or more waves traverse the same region, they obey the superposition principle. That just means they add together. If I wanted to take two example waves here, so for example two cosine waves, and add them together, then I would have that be psi1 plus psi2 is equal to a cosine k1x minus omega 1t plus a cosine k2x minus omega 2t. For simplicity's sake, I'm going to keep the amplitudes the same. And the wave numbers are k1 and k2, and the angular frequencies are omega 1 and omega 2. Now if I want to do this, it helps to use the trigonometric identity. Okay? And I show the identity here. Cosine alpha plus cosine beta is equal to 2 cosine of 1/2 alpha plus beta times cosine of 1/2 alpha minus beta. So if I use that identity, then apply it to my problem above, then I end up with psi is equal to psi1 plus psi2, which is equal to 2a cosine delta kx over 2 minus delta omega t over 2 times cosine of k average x minus omega average t. Here I'm defining delta k as k1 minus k2, the subtraction of the two wave numbers. Similarly for delta omega, and also k average is k1 plus k2 over 2, similarly for omega average. Okay? So that's what I get mathematically. Now if I were to plot that out into a little cartoon and just look, say, at one segment of my wave, then it would look like this little cartoon right here. Now, each one of these cosine terms that are multiplying by one another represent a different part of this picture. The cosine delta k's and delta omegas, that's the envelope, which is represented here by a dashed line. Now, in the real wave packet, that dashed line wouldn't be there, and you just see the blue. But the dashed line here helps guide your eye. Basically, what this part does is modulate the amplitude of our wave, okay? So it defines the envelope. Now this cosine k average and omega average term, that's our blue here, okay? Now we call these two things different. This dashed line represents the group, and the blue is the phase, okay? So if you look at these two cosine terms, you can see that we could calculate a velocity from each one of these guys. Now the phase would be omega average over k average, and that's the blue. Okay? Whereas the group velocity is delta omega over delta k, okay? And that's the dashed line. Now, these two numbers don't necessarily, of course, have to be the same. The group and the phase velocities can be different numbers. We'll come back to that idea in just a minute. So here's another picture of the envelope, and the envelope here indicated by the dashed line, and of course they can travel at different speeds. Now the classical analogy to all this is the idea of beating. Now you might use this to tune an instrument, for example, but for today I'm going to do a little demo for you with just some tuning forks here. Now one of the tuning forks is got a little bit of modeling clay stuck onto the side, and that's going to alter the frequency slightly. Other than that, the two tuning forks would have the same frequency. So let me hit them for you, and then you can hear what I'm talking about. So what you're hearing is called a beat, and that's a modulation of the amplitude. See, I have these two frequencies here, basically in the same place at the same time, and they're really close together, only altered a little bit by the clay. And so they obey the superposition principle and they add together. And when they do that, that envelope is created, and that envelope gives you your beating. If you were to draw a picture of what that looks like, it might look like this. So you have your blue and your black, and those are the two slightly different frequencies. And then, of course, the envelope here gives you the beat. All right? Now, the human ear can detect a beat frequency of up to about 20 beats per second. And that beat frequency equals the difference between the frequencies of the two sources shown here by this little envelope. Okay? So that's the classical analog. Now, getting back to matter waves, as a wave packet becomes confined to a limited region in space, delta x, it takes a larger range of wavelengths or wave numbers to create the packet, which is delta k. Likewise, as the packet's duration in time is narrowed, delta t, then the number of frequencies that makes the group gets larger. So if you want to express that mathematically, then you'd end up with delta x, delta k is approximately equal to 1, and delta t, delta omega, is also approximately equal to 1. Now, this actually forms the basis for the Heisenberg uncertainty principle, okay? So here, if you wanted to plug in delta x, delta k, remember k is 2 pi over lambda, and lambda is h over p, where h is Planck's constant and p is the momentum. So if I plug in for that, then I end up with delta x, 2 pi delta p over h is approximately equal to 1, okay? So then when I solve delta x, delta p, that's approximately equal to h over 2 pi. And that's a number that we like to call Hbar. So anytime you see Planck's constant divided by 2 pi, that gets used a lot, and so people actually gave it a name and a symbol with an H with a line through the stem, and that's called Hbar. So the localization of the wave packet over a small region to describe a particle requires a large range of wave numbers, and conversely, a small range of wave numbers can't produce a wave packet localized within a small distance. So that's Heisenberg's uncertainty principle, and we're going to talk a lot more about that in the next lecture. But for now, let's return to this idea of the wave envelope and the fact that the group velocity and the phase velocity don't have to be the same. So I have a little figure to demonstrate that, to help you visualize it really. Here's an envelope with a phase inside of it. The envelope here is represented in blue and the phase in orange. And you can see that these two things are traveling at different speeds. Actually, the phase in this case is faster than the group. Okay, so that's what that looks like. You can see it looks like the phase is moving through the group, but both of them are moving to the right. Now, if I give you a different example, in this example, the group is moving faster than the phase, and so it looks like the phase is moving backwards as everything still moves to the right. Okay, so this kind of helps you visualize what I'm going to be talking about in the next example. Okay, so these relationships between omega and k and the velocities, they make up what's known as the dispersion relationships. Now for our two simple waves that we added together, we had that omega over k average is equal to the phase, and that our group velocity was delta omega over delta k. Now that's for two, but if of course you have a lot more waves, then that delta starts to shrink and shrink and shrink and becomes a derivative. And so your group velocity would be d omega dk, where you're taking the derivative with respect to k of your angular frequency. Now remember, the group velocity can be greater or less than the phase velocity. But if you have what's called a non-dispersive medium, then the phase velocity is the same for all frequencies, and it's also going to be equal to the group velocity. Now to give you sort of a classical picture for what this is like, we can talk about dispersion for light. Now, dispersion actually causes rainbows. In a dispersive material like glass or water, the index of refraction is going to vary with the wavelength, and different colors of light travel at different speeds. And that's why light that travels through a glass prism gets separated into its component colors. And it's also why when sunlight strikes raindrops, it splits it into little rainbows as well, okay? And then eventually, with enough raindrops, you get a big old rainbow up in the sky. So that's dispersion, classical. Getting back to sort of a non-classical quantum particle though, let's talk about what the group and the phase velocity for a non-relativistic free electron would be. Okay, so here we go. The phase velocity is equal to omega over k. And we know that electrons are also waves, particles and waves. So de Broglie waves have an energy E is equal to hf, which is hbar over omega. Remember that the angular frequency and the frequency are related to one another via 2 pi. So here we also know that lambda is equal to h over p, which is equal to 2 pi over k. So we can relate the wave number to the momentum directly via the relationship k is equal to p over h bar. So I can substitute into my phase relationship omega over k for my values for E and P. So omega over k is equal to E over h bar divided by p over h bar. Now the h bars cancel out and that leaves E over p. Now for a non-relativistic free electron, the energy is going to be just the kinetic energy because it's not in a bound system, so there's no potential energy. And remember that the kinetic energy for a non-relativistic particle is p squared over 2m. So then E over p becomes p squared over 2m divided by p. And then that becomes p over 2m. And remember that classically the momentum p is equal to mv. And then you have mv divided by 2m, and the m's cancel, leaving v over 2. So the phase velocity for a non-relativistic free electron is half of the speed of the electron itself. Now let's solve for the group. The group velocity is d omega dk. Now, using the same ideas we had on the previous page, remembering that E is equal to h bar omega, then d omega is dE over h bar, and dk is dP over h bar. And that means that our group velocity is dE dP. Okay, so we're taking the derivative with respect to the momentum of the energy, ddP of the non-relativistic kinetic energy there, which is p squared over 2m. So when I take the derivative of that, I get 2p over 2m, and then the 2's cancel, leaving mv over m, and the m's cancel, leaving v. So what that means is the group speed matches the speed of the particle. And that makes sense, right? You want your wave packet to track with where your particle actually is. And we can see here that the group velocity is faster than the phase velocity here. All right, so that'll do it for dispersion relationships and wave packets. And then we're going to talk about some of the consequences for that, the fallout, basically, which is the Heisenberg uncertainty principle, in the next lecture.